In space, there is no sound, no wind, no echo, no whisper of movement, only silence. And yet, inside a spacecraft traveling nearly 40,000 kilometers per hour, something will be thinking. Not loudly, not emotionally, not dramatically, but precisely. A microchip, smaller than your thumb, quieter than a breath, yet powerful enough to guide human beings around the moon and bring them home. This is the silent brain of Artemis II. More than half a century ago, humanity left footprints on the lunar surface. Through the legendary Apollo program, astronauts crossed the void and stepped into history. Then, we stopped. For 50 years, no human has traveled beyond low Earth orbit. Until now. Under NASA's Artemis program, a new era begins. Artemis II is not a landing mission. It is a proving ground, a test of systems, a rehearsal for permanence, a gateway to Mars. But unlike Apollo, this mission depends on something far more advanced: computing. Not room-sized machines, not slide rules, but microscopic architecture carved into silicon. And inside that silicon lies survival. On Earth, your smartphone contains billions of transistors. They switch on and off billions of times per second. They stream videos, play music, process images. But take that same phone and send it beyond Earth's protective magnetic field, it would fail quickly. Space is flooded with radiation, charged particles from the sun, cosmic rays from distant galaxies. When these particles strike a microchip, they can flip a single bit of information. A 0 becomes a 1. A 1 becomes a 0. On Earth, that might crash an app. In space, it could miscalculate a trajectory, fire a thruster at the wrong time, or misread oxygen levels. So the microchips aboard Artemis II are not ordinary chips. They are radiation-hardened, engineered not for speed, but for resilience. Let us shrink, smaller than a grain of sand, smaller than a human cell. Now we are inside the microchip. We see layers, silicon substrate, metal interconnects, insulating barriers, billions of microscopic transistors, each acting as a switch: on, off, 0, 1. These switches form logic gates. Logic gates form circuits. Circuits form processors. Processors execute instructions. Instructions control spacecraft systems. This is how thought becomes action. Within the chip are processing cores, memory arrays, input-output controllers, redundant mirrored systems. Every critical pathway exists more than once, because in space, backup is survival. Inside the Orion spacecraft, these chips work continuously. They calculate orbital mechanics. They adjust orientation using reaction control thrusters. They monitor cabin pressure, carbon dioxide levels, temperature stability. When astronauts press a button, the command travels as electrical signals. The chip interprets it, validates it, executes it. If communication with Earth is delayed, the spacecraft must decide on its own. Autonomy is not luxury, it is necessity. The moon is 1.3 light seconds away. That delay matters. So the microchip thinks locally, quietly, instantly. Space temperatures can swing from 120 degrees Celsius in sunlight to minus 150 in shadow. There is vacuum, no air, no convection cooling. Heat must be managed through conduction and radiation. Then comes solar storms. Massive eruptions from the sun can release energetic particles powerful enough to disrupt electronics.
Engineers simulate these storms on Earth. They fire radiation beams at the chips. They expose them to extreme conditions. They attempt to break them. Because once Artemis 2 launches, there is no reset button, no technician floating nearby, only silence, and the chip must endure. In deep space engineering, failure is assumed. That is why Artemis 2 uses triple modular redundancy. 3 processors run identical calculations simultaneously. If one disagrees, it is outvoted. Error correction codes scan memory constantly. Watchdog timers monitor system health. Fault detection systems isolate malfunctioning components. This is not paranoia, it is preparation. Because the microchip carries responsibility heavier than its own weight. Human lives depend on stable computation. Your gaming processor may run at billions of cycles per second. Space processors often operate slower, older designs, larger transistors. Why? Because smaller transistors are more vulnerable to radiation. Speed increases fragility. In space, reliability matters more than performance. Stability beats speed. Consistency beats innovation. The Artemis 2 microchip may not win benchmarks, but it will win something far more important: trust. Today, the chip guides astronauts around the moon. Tomorrow, it may manage lunar habitats, control robotic construction systems, enable artificial intelligence to assist deep space crews. And one day, a descendant of this microchip may help humans reach Mars. From Apollo's primitive guidance computer to Artemis's resilient processors, human exploration evolves. Silicon becomes companion. Code becomes co-pilot. Somewhere inside Orion, beneath shielding and aluminum walls, a microscopic circuit will activate. Electric current will flow. Transistors will switch. Instructions will execute. And in the silence of space, that tiny pulse of electricity will carry the hopes of humanity. Not with noise, not with celebration, but with precision. Because sometimes the most powerful force in the universe is not a rocket launch. It is a silent calculation inside a microchip.